Okay, rotational dynamics. First question. A string is wound round a wheel while its free end is tied to the ceiling as shown in the figure above. The wheel is released from rest so that it starts to rotate and moves downwards. Assuming the wheel as a solid disc with mass 2 kg and radius 30 cm, determine the linear acceleration of the wheel, the tension in the string. Okay, so now we have the rotating object and it's rotating downwards. This wheel is getting faster and faster, definitely. It has acceleration. Okay, see here it has acceleration. So this rotational dynamics is about Newton's second law. We will use acceleration. Acceleration means it has a resultant force. The resultant force is not zero, but the total force, the resultant force, there is a net force or resultant force equal to ma. Total F equal to ma, Newton's second law. Now we translate to the rotational terms. We call total torque equal to I alpha. No, the I is like the mass, moment of inertia. I is the moment of inertia, just like mass. And then alpha, angular acceleration, is just like the linear acceleration. The torque is like force. Okay, torque is like force. So, okay, so we have the mass, given the mass, the radius, change to meter. And of course, because we are going to use total torque equal to I alpha, we need the moment of inertia. Moment inertia is just like the mass. So we need to find the moment inertia of the solid disc. He mentioned that this is a solid disc. Sorry. Okay, so this is a solid disc. So we need to use the solid disc formula. Okay, so solid disc, the formula of moment inertia is half mr square. Okay, half mr square. So let us find out what is the moment of inertia for solid disc. Given the mass, just put the mass, the radius, 0.3 meter. Okay, so cut them. So I will get 0.09 kilogram meter square. Kilogram meter square is the unit for I, moment of inertia. Okay, so I got the moment inertia. Now, let's draw the free body diagram. You must draw a free body diagram. Okay, so what force acting on this wheel? You know, our subject, which is in our focus now, is the wheel only. So let's draw the forces on the wheel. Okay, what force we have here? The wheel itself, it has the weight, of course, the weight of the wheel, and then in the string, it has tension. Of course, here has tension, but this is not our focus. The wall is not this. I mean, this tension acts on the wall. The wall is not our focus, so we don't consider the tension upward here. Yeah, we don't consider this one. Only this tension we need, because our subject, our focus now is only the wheel. So we only take this tension. Okay, this tension can be neglected because this tension acts on another object, which is the wall. So I think only two forces. Yeah, and then don't forget you must draw the acceleration downward, and at the same time it has angular acceleration. Yeah, it rotating anti-clockwise. Okay, so yeah, this is the diagram. I redraw here. So this at the top part we no need to consider. Yeah, that is not our focus. Our focus is only the wheel. Okay, the weight, the tension, angular acceleration. All right. Don't forget you need to put the sign. Follow the acceleration positive, opposite acceleration negative. For angular acceleration also the same. Follow acceleration positive, opposite acceleration negative. Okay, positive, negative. Follow acceleration, positive. Opposite angular acceleration, negative. Okay, now let's do we have two. One, we have the acceleration, and the one we have angular acceleration. So let us do the total F equal to ma first. Yeah. So for this one, total F equal to ma, what force involved? We have the weight downward, tension upward. Okay. So which one followed the acceleration? The weight. So the weight is positive. Tension is opposite acceleration, so negative. So just put in. So the weight is positive because follow acceleration. Tension is negative because opposite acceleration. Okay. So we got it. So what is the weight? What is the weight? Oh, 2. Okay, the weight is mg. So mg, so 2g. So the mass is 2 kilogram. So, and then tension we don't have. Then 2a, mass is 2. Okay. So, we have two variables, tension and acceleration. So we need to do the total torque equal to I alpha in order for us to do simultaneous equation. So now for torque, we need an axis of rotation. Okay, we need axis of rotation. So this thing rotate around the axis of rotation. So the axis of rotation is at the center. So again, W has no torque. W has no torque. Why? The torque for W because is okay. Again, this is the W R sine theta. Again, this R is 0. Yeah. So that's why the torque for the weight is 0. Because the weight acts on the axis of rotation itself. So the R is 0, no R. So torque equal to 0. Yeah. When the thing is at the axis is at the when the force is at the axis of rotation, so it can't rotate the object at all. You see, it can't rotate the object at all. So when R is 0, torque is 0. Okay. When the force is at the same point as the axis of rotation, it has 0 torque. Now, tension. Tension has the torque. Okay. So how far is it from the axis of rotation? How far is it? Yeah, it is distant r, or called the radius of the wheel, the wheel radius, isn't it? The wheel radius, this one, yeah, the wheel radius, which is 30 cm, 0.3 meter. So we can say this is 0.3 meter. Now, and then another thing, this is perpendicular, 90 degree. So straight away we can just, the answer is T times R. Okay, T times R, straight away. Or you can say it is sine 90. Sine 90 equal to 1, right? So T times R sine 90. Yeah, sine 90 is equal to 1. Yeah. So you don't write the sine 90 also, never mind. And then, okay, so our moment inertia, we got it just now, actually. Moment inertia, we got 0.09, okay, 0.09, and then alpha. All right, alpha. The question asks for linear acceleration. A. So, since the question asks for linear acceleration, we don't want alpha. So what do we do? What if we don't want the alpha? We change the alpha to a. We change the alpha to a over r because the question asks for linear acceleration. So linear, as a lah. So we need the a. We don't want alpha. So you can change the alpha become a. So a equal to r alpha. So that's why alpha equal to a over r. But if the question asks for angular acceleration, then if the question asks for angular acceleration, then you need to use alpha. In that case, you just change the A become R alpha. Okay, so all depend on the question asked for what is required. Yeah. So now it asks for A, so we did A. We change alpha to A. Okay, now we have PR. Okay, R just multiply above. Okay, R just multiply above. So here we have TR square and TR square, and then we have 0.09 A. Okay? Yeah. So, okay, we have the R, which is 0.3 meter. So let's substitute. 0.3 square equal to 0.09 A. 0.3 square equal to 0.09. So our tension is actually A itself. Okay, so let us do. Okay, 2G. Let's find our tension is A. So just change to A. So we got 3A equal to 2G. 3A equal to 2G. Yes. So what is our A? Our A is 6.54 meter per second square. That's our acceleration. So our tension also equal to A, which is 6.54 Newton. So our A, we got the answer for A, part A. And we also got the answer for part B, the tension in the string. The tension in the string. So this is the answer for part B. The answer 6.54 for both. Okay. So is it correct? Yes. All right. That's how you do the questions in rotational dynamics. See you in the next videos. Bye.